Good morning, students. Let's start the new and the last chapter of the calculus, which is a differential equation. First of all, you all know what is meant by an equation. An equality is equals to will be there. Some LHS and RHS will be there. Then it is said to be an equation. As far as x square plus 2x plus 1 equals to 0, which is a equation in terms of x. So it is said to be a quadratic equation. Likewise, so sine square theta plus 2 sine theta cos theta is equals to 1. This is also an equation which is in terms of a trigonometric identities. Therefore, it is said to be a trigonometric equation. Likewise, differential equation. So a differential equation is an equation which contains one variable, one dependent variable, one or more independent variables, and the differential coefficients or the derivatives of one dependent variable with respect to independent variables is called the differential equation. So our new chapter is a differential equation. Differential equations. So first of all, the definition of this is an equation involving one dependent variable, an equation involving a dependent variable, one or more independent variables, and their derivatives of a dependent variable with respect to independent variable is called, or variables is called, a differential equation. First of all, what is meant by a derivative? A derivative is nothing but rate of change of derivative, means dy by dx. A rate of change of y with respect to x. So what is dy by dx? A rate of change of y with respect to x. What is meant by acceleration? Acceleration is nothing but rate of change of velocity by rate of change of time. That is d by dt of v, otherwise dv by dt. Acceleration a is equals to, that is rate of change of velocity with respect to time. Here time is independent variable and v is depending on t. So here t is independent variable and v is depending on t. So we can have some examples. X dy by dx plus y equals to 0. So here one variable is there and the derivative of y with respect to x. The derivative of dependent variable with respect to independent variable is there. Otherwise, we can even take x square d square y by dx square plus 2xy dy by dx plus 3 equals to 0. So here this is an equation. Since equality symbol is there and here xy variables, and here in the if these two equations if you consider, so in everything actually here dy by dx. This is the derivative of y dependent variable with respect to independent variable is there. Here d square y by dx square. This we got by derivative of d by dx of dy by dx. dy by dx is the first order derivative as we have studied before in the last year, intermediate first year. So x square d square by dx square likewise. And third one 2x minus 3y d square y by dx square whole square minus of 3x plus 2y dy by dx is equals to 0. And we can even take dou square u by dou x square plus dou square y by dou y square is equals to u. Otherwise, so x square dou square u by dou x dou y plus y square dou square u by dou y dou x is equals to 2u. So these are some of the examples of this differential equation. In everything is equals to symbol is there. That means it is an equation first of all, and everything is in terms of the values, the variables x and y. Here y is independent variable and x is the dependent variable. So here dependent variable independent and the derivatives of dependent variable with respect to independent variables. That means it may be one variable or more than one variable, independent variables as far as this is concerned. So here independent variable is 1. Here independent variable is 1. But if you consider here there are two independent variables. So therefore we can classify this differential equations can be classified into two categories. What are they? Ordinary differential equation, and one is partial differential equation. So what is ordinary differential equation? An equation involving the derivative of one dependent variable with respect to only one independent variable. So as far as the first three cases are concerned, these are all the derivative of one dependent variable with respect to only one independent variables here. Only one. But as far as partial differential equations are concerned, an equation involving one dependent variable with respect to one or more independent variables. As far as these are concerned, here u is the dependent variable. So with respect to one or more, here x and y are both independent variables. Therefore, we can classify differential equations in these two categories: ordinary differential equation, partial differential equation. So we will confine to ourselves with the ordinary differential equations. So we can study this partial differential equations in the higher classes. So we will confine ourselves to differential equation. As long as ordinary differential equation is given, that is to be understood as a ordinary differential equation only. So these are what we have discussed so far. Ordinary differential equation, an equation involving derivatives of the dependent variable with respect to only one independent variable. See, the derivative means d by dx of. So here d by dx of dependent variable is y with respect to only one independent variable x. So such kind of, these are the examples of ordinary differential equations, where in both the examples, here we see the dependent variable is only one, which is independent variable is only one, which is x. Dependent variable is one, which is y. So independent variable is one and only one, which is x. Partial differential equation, an equation involving derivatives of the dependent variable. What is the dependent variable? Here, in this case, u. Dependent variable with respect to more than one independent variables. Here, x as well as y, more than one. Here, in the first case, x is the only independent variable. But that is not the same case when it is a partial differential equation where the number of independent variables is more than one. So sometimes actually 3, 4 also we can have. So this is the example for partial differential equations. And the next topic is order of the ordinary differential equation. The order of an ordinary differential equation is defined to be the order of the highest order derivative occurring in it. So last year we have learnt the first order derivative is, so differentiating y with respect to x is dy by dx. Likewise, differentiating dy by dx with respect to x is, this time it is d square y by dx square. Likewise, differentiating d square y by dx square with respect to x is d cube y by dx cube. Likewise, differentiating, we can differentiate any number of times like this. So differentiating y with respect to x is dy by dx is also termed as y1 or y dash or simply d dash, etc. This is what we have learned last year. Now d square y by dx square is simply, it can be termed as y2 or y double dash or d2. Okay, d square or d square. Okay. So likewise, d cube y by dx cube y2 y triple dash d cube. Likewise, nth derivative is d power n y by dx power n. This can be written as dn, or this is yn, or this is yn. So actually this is what we have learned. This is the first order derivative. This is the second order derivative. This is the third order derivative. This is the nth order derivative. So now, how do we evaluate the order of the differential equation? For example, if you take one example x dy by dx plus y square d square y by dx square whole square plus 3xy equals to 0. For example, this is the differential equation. Which differential equation? Ordinary differential equation. Already I have told the differential equation is ordinary differential equation only. The partial differential equation we are not discussing it here. So now x dy by dx plus y. So this is equals to symbol is there. Therefore, it is a differential equation. Point number 1. So here, what is how many independent variables are there? Only one. So x. Okay. So if the number of independent variable is only one, then it is said to be ordinary differential equation. Now, see this here. This dy by dx is the first order derivative. D square y by dx square is the second order derivative. So which is highest derivative in these two? Obviously d square y by dx square. So therefore its order is equals to 2. So for example, if you take another example like x or dy by dx whole power 100 plus d square y by dx square x d square y by dx square plus 3y is equals to 0. For example, if you take this is the differential equation. To be more specific, ordinary differential equation where number of independent variable is only one. So this is x here. So this is first order derivative, this is second order derivative. So which is highest? The second order derivative. Otherwise, for example, 3y d cube y by dx cube is equals to 0. Now the order here is 3. Now the next concept we are going to discuss is a degree. What is a degree? The power or exponent. The power or exponent of the highest order derivative is nothing but degree. But prior to that, actually we have to discuss a few more things, because as far as order is concerned, order is easy, okay. But as far as the degree is concerned, so first of all, that differential equation must be a polynomial of the derivatives. First it has to undergo that, and at the same time the powers of the derivatives, should be a positive integers. So it should not be like a fractions. So first of all, actually first we have to clear all these things. Then whatever the polynomial equation of the derivatives we are going to have ultimately, then the degree is defined to be the power or the exponent of the highest order derivative is nothing but a degree, which we will be discussing later on. Now the degree. The degree of the highest derivative involved in an ordinary differential equation, when the equation has been expressed in the form of a polynomial. So underline this, polynomial. So the polynomial, polynomial is the form f of x equals to a0 x power n plus a1 x power n minus 1 plus a2 x power n minus 2 etc. plus an, where a0 not equals to 0 and an is said to be constant, a0, a1, a2 etc. are said to be coefficients, with the power being the powers n, n minus 1, n minus 2. These are all the non-negative integers. Okay, so here there is no fraction you can see here. If it is a fraction, then it is not said to be a what is that? So polynomial. So examples for this is x square minus 1 equals to 0. This is the polynomial of degree 2. Likewise, x cube minus 3x square plus 2x minus 4 equals to 0. This is another example for a polynomial whose degree is 3. It's a cubic polynomial. X power 4 minus 3 equals to 0. It is a biquadratic polynomial whose degree is 4. So therefore n is what? Should not be in the fractions. That's what here. Polynomial in the highest derivative. So here polynomial in the derivatives, in the highest derivatives. That means here d square by dx square 2 dy by dx whole square plus 5y is. So this example, if I take, for example, what is the degree of this? This is the first order derivative. This is the second order derivative. So now which is the highest derivative? Second order. Second order derivative's power. This is how much? 1. So therefore the degree of this is 1. But see here, the degree of 5 plus dy by dx whole square plus 5 by 3 is equals to 2 d square over dx square. So we cannot jump to a conclusion that d square over dx square power is 1, therefore degree is 1. So we should not, because this is not the polynomial in terms of the derivative. So here, if you see, the power of this is 2 5 is a 10 by 3. So 10 by 3 is a fraction. So here, by eliminating radicals and fraction powers, whatever the fractions are there, we should eliminate it by suitable by suitable powers on both the sides, squaring on the both sides, cubing on the both sides and all. So if I do 3 by 5 here, for example, then whole power 3 by 5, then so 5 cancel, 3 cancel. Okay, it is non-fraction now. But here d square over dx square, derivative's power is a fraction here. So we should not do like that. Therefore, it is not correct. So what more we can do is cubing on both sides we can do. Cubing on both sides. Then this 3 gets cancelled. Therefore, I am left with a whole power 5 here. So 2 5s are 10. So here d square over dx square whole cube. So this is the first order derivative. This is the second order derivative. The highest order derivative's power is nothing but a degree. So therefore its degree is 3 now. So here the degree of dy by dx plus sine dy by dx equals to 0 is. So this is not a polynomial in terms of a derivative. Dx in sine function. So this is, first of all, it's not, we cannot express. So with some efforts we can express this fractional power into the integer here. But actually we cannot do anything to make this into the polynomial. Therefore, its degree is undefined. Now, the formation of differential equation. We discussed the formation of differential equations through some illustrations and arrived to the general case. So, consider the single parameter equations. So, for example, y is equals to mx plus 6. This, as you all know, this is the family of straight lines. Family of straight lines having slope m and y-intercept 6, where m is a parameter or arbitrary constant. Arbitrary constant. So the family of all the differential equations of this can be formed by eliminating this parameter through the process of differentiation. So, differentiating y with respect to x on both sides. So, dy by dx is equals to m. Substituting m in the first equation, then we will get y is equals to, what is m? dy by dx into x plus 6. Therefore, this is the family of all straight lines having slope m. But if you see 1 and 3, both represents the family of straight lines. But one is devoid of the derivatives and 3 is the devoid of the arbitrary constants. So consider the 2 parameters case. For example, y is equals to a e power x plus b e power minus x. So here a and b, there are 2 parameters, arbitrary constants, for which we need to differentiate it twice so that a and b parameters will be eliminated. Therefore, dy by dx is equals to a e power x minus b e power minus x. Again differentiating, because there are 2 parameters are there for which we need to differentiate it twice so that the parameters, both the parameters a and b, are to be eliminated. So again differentiating with respect to x on both sides. d by dx of y is dy by dx. d by dx of dy by dx is second order derivative d square y by dx square is equals to a e power x derivative is e power x minus b e power minus x derivative is minus e power minus x. Therefore, this is a e power x plus b e power minus x. Therefore, this is the first equation, and therefore d square y by dx square is equals to, what is this a e power x plus b e power minus x? This is y. Therefore, d square y by dx square minus y equals to 0. Therefore, this is the differential equation of the family of all curves following y equals to a e power x plus b e power minus x. If you see, both 1 as well as 3 or 3 represents the family of curves, but 1 is devoid of the derivatives and the third is devoid of the arbitrary constants. This process of forming a differential equation from the original equation, y is equals to mx in the first example, y is equals to a e power x plus b e power minus x in the second example. Those are the original equations. From these original equations, forming a differential equation is nothing but formation of a differential equations. If the differential if the equation contains n arbitrary constants, therefore we need to differentiate n times to eliminate all the arbitrary constants. Let us discuss the solution of a differential equation. For this, let us take two examples that we are familiar with. X square minus 3x minus 4 equals to 0. Sin x plus cos x is equals to root 2. So, the solutions of these two equations are numbers. It may be either a real number or a complex number. So, if you solve these two numbers, we will get a number that will satisfy the given equation. That means the number, when we substitute it back in the given equation, then LHS is equals to RHS. For example, x square minus 3x minus 4 equals to 0. If you solve, then x square minus 4x plus x minus 4 equals to 0. X into x minus 4 plus 1 into x minus 4 equals to 0. So, x plus 1 into x minus 4 equals to 0. So, therefore, x is equals to minus 1 or 4. So, these are the numbers. These two are what? Numbers. These are the solutions or roots of this given equation. Why? Because when we substitute these numbers back in the given equation, then this will satisfy. LHS is equals to RHS. So, for example, minus 1, if you substitute here 1, minus of minus plus 3 minus 4 is equals to 0. So, 4 when we substitute back in this, 4 square 16, minus 3 4s are 12, minus 4. So, 16 minus 16 is equals to 0. Likewise, if you solve this, sin x plus cos x is equals to root 2. So sin x plus cos x, this can be written as 1 by root 2 plus cos x into 1 by root 2 that we have done in the last year. So root 2 by root 2. That is, I just divided with root 2 on both the sides. Then this is sin x cos pi by 4 plus cos x sin pi by 4 is equals to 1. So this is equals to sin of x plus pi by 4 is equals to sin 90 degrees. So x plus pi by 4 equals to sine 90 degrees is pi by 2. Therefore, x is equals to pi by 2. 90 minus 45 is pi by 4. You substitute back in this given equation. Then sine pi by 4 is 1 by root 2 plus cos pi by 4 is 1 by root 2. This is 2 by root 2. This is equals to root 2. Therefore, the solutions of these two equations are numbers. So, these numbers which will satisfy the given equation. So, what I mean to say is the solutions of these are numbers. Now, let us consider d square y by dx square plus y equals to 0. In contrast to the above two examples, where after solving we get a number that will satisfy the given equation. That is, when the value is substituted back into the given equation, then LHS is equals to RHS is satisfied. In the same way, d square y by dx square plus y is equals to 0. In contrast to the above examples, so the solution of this is a function. There, the solution of the equation is a number. So the solution of this differential equation is a function phi. So that will satisfy the given equation. Y is equals to a sine x plus b. So where a comma b are any real numbers. So now if you differentiate it, y is equals to a sine derivative is cos x plus b. Now, and this is dy by dx, and d square y by dx square is equals to a minus sine x plus b. Now this y dy by dx, d square by dx square, these values if you substitute in this given equation, then it is satisfied. Therefore, this y is equals to a sine x plus b, which is the function of x, satisfies the given equation. Therefore, this a sine x plus b is said to be, so y is equals to a sine x plus b is getting satisfied after substituting in this. And if y is equals to 2 sine x plus pi by 4 if I take, then dy by dx is equals to 2 cos x plus pi by 4, and d square y by dx square is equals to minus 2 sine x plus pi by 4. So now y dy by dx, d square by dx square substitute back in the given equation. Here also it is satisfied. Therefore, a sine x plus b is said to be the solution of this differential equation, and 2 sine x plus pi by 4 is also said to be a solution of this differential equation. But as far as a sine x plus b, where the solution which contains two arbitrary constants a and b is said to be, this is the general solution of the differential equation. And not only that, this also satisfies y is equals to 2 sine x plus pi by 4 in this equation. This is said to be the particular solution of the differential equation. Therefore, we can arrive to this concept that function phi, that is y is equals to a sine x plus b, consists of two arbitrary constants a and b, are called parameters, is called the general equation, general solution of the given differential equation. y is equals to a sin x plus b, since it contains a and b, two parameters. So hence this is said to be the general solution of a differential equation. Why? Because since a and b are two arbitrary constants for which we have differentiated twice and substitute back in the given differential equation in this, then this has satisfied this equation. Therefore, this is said to be the general solution of the given differential equation. And so here a is equals to 2 and b is equals to pi by 4 we have substituted. Then y is equals to 2 sin x plus pi by 4. So again we had differentiated and substitute back in this equation. This also satisfied like this. So here the function y is equals to 2 sin x plus pi by 4 contains no arbitrary constants like this. Here a and b are the arbitrary constants. Here we don't have any arbitrary constants, but only the particular values of the parameters a and b, and hence it is called particular solution. This is the general solution and this is the particular solution. Both satisfied the given differential equations. Thus, we can arrive to a conclusion that the solution which contains the constants, which contains the arbitrary constants, is called the general solution or primitive of the differential equation, and the solution free from the arbitrary constant, that is the solution obtained from the general solution by giving particular values to the arbitrary constants, is called a particular solution of the differential equation.